Hello everyone, good morning, good afternoon, and good evening, depending on where you are located. Welcome to the ISRM lecture series on deep mining. In this video lecture, I'm going to talk about various available precondition methods. And in particular, my lecture is focusing on new precondition technique for deep mining. I will start with giving a bit of introduction to myself. I'm Ranjith Pathegama, Professor in Sustainable Development of Technologies for Resource Recoveries at Australia's Monash University. I'm a Fellow of Australian Academy of Technology and Engineering and Editor-in-Chief of Geomechanics and Geophysics of Geoenergy and Georesources, a Springer Nature journal. I'm the founder and a director of Geomechanics for Geoenergy and Georesources Deep Research Laboratory at Monash University. My primary research aim is to facilitate collaborative research, both fundamental and applied, assessing feasibility and resolving technical problems in harnessing new and more sustainable forms of deep earth mineral and energy resources. My research areas include CO2 mitigation, unconventional oil and gas, deep geothermal energy extraction, development of new technologies for future mining, and create a new value chain from waste to wealth. Further details of my research can be found in www.3gdeep.com website.
This lecture is structured as follows. I will start with existing precondition methods, followed by an introduction of new technique, which is slow releasing energy material agent, commonly known as SREMA. I will then discuss the details of this compound, its properties, its compositions, and how it works, and finally, the future applications of SREMA. First, I would like to give you a brief introduction to the need for deep mining by addressing the elephant in the room. As we all know, resource consumption is increasing rapidly due to the growth of the global population and the creation of new products and markets. This causes the global demand for minerals to increase exponentially, leading to decline ore grades. Consequently, mining volumes are progressively increasing, and underground mining continues to progress to greater depths to sustain the supply for the growing demand. Therefore, rock preconditioning is required to treat the rock mass at greater depths, which enhances efficiency of the mineral recovery and extraction process and mitigates rock burst due to the higher stress conditions. Simply put, rock preconditioning is the process of artificially inducing changes to the rock mass. And in preconditioning, the rock is broken into fragments due to the reduction of rock mass strength by inducing microcracks. 5 mainstream rock preconditioning techniques available to the industry. They are number 1, drilling and blasting, number 2, hydraulic fracturing, number 3, microwave induced fracturing, number 4, plasma channel drilling, and number 5, thermal stimulation. We will look at all these preconditioning techniques in details in the next few slides. In drilling and blasting, preconditioning is achieved by placing explosives in holes drilled in the rock mass, damaging the intact rock and extending existing discontinuities. The damage mechanism alters the in situ mechanical properties and mass properties of the rock material, such as strength and stiffness of the rock mass. This method is most primitive and economically viable technique used in rock fragmentations. The second preconditioning technique is hydrofracturing, or better known as fracking. In this method, fractures are created by injecting pressurized liquid into a rock mass through a pre-drill borehole. A fracture is created in the fabric when the fluid injection pressure exceeds the effective strength of the rock mass. In the oil and gas industry, fracking is commonly used to induce cracks in deep rock formations to enhance permeability, thereby increasing the efficiency of recovery. In the caving mining industry, fracking is used to precondition the rock mass by introducing large-scale fractures treated as additional joint sets. Of the fluid-based fracturing methods, the most common is where water is used as a fracture fluid. In this method, various combinations of water, chemicals and propellants are used to increase the fracture apertures of deep underground rock formations following hydraulic fracturing. General combination is 99% water plus propellants and 0.5% of other chemical additives. Hydraulic fracturing is a cheap and promising method to transport propellants deep into reservoir, which stimulate fractures and props them open for subsequent production. However, hydraulic fracturing utilizes a vast amount of water. A typical shale gas well injects between 2 to 4 million gallons of water into a deep shale reservoir, followed by high water disposal cost. Also, water leakage into groundwater aquifers is unavoidable in most cases, since the direction of an induced hydraulic fracture is dependent on the existing natural rock fracture network and the in-situ stress conditions. This fact, coupled with added chemicals, poses the threat of pollution of groundwater aquifers. So to eliminate some of these drawbacks, liquefied natural gas can be used instead. In the following slides, I would like to discuss these alternative fracking fluids. The world is emitting around 35 billion tons of CO2 annually to the atmosphere, causing the climate change. So we need to find ways to use CO2 for mineral and energy industry during the recovery phase of resources. Supercritical CO2 is a well-known alternative fracking fluid with various advantages. As you can see in the phase diagram of CO2, when the carbon dioxide is held beyond supercritical conditions of around 31 degrees C and 7.5 MPa pressures, CO2 becomes supercritical state. In other words, it flows like gas with the density of a liquid. On the upside, this method reduces water consumption and increases gas production due to miscibility with hydrocarbons. Also, supercritical CO2 induces the reservoir to produce multiple and complex fracture networks, which enhance the fracking effect. In addition, effective gas displacement from fractures with poor connectivity can be achieved. Further, we can simultaneously achieve carbon sequestration, contributing to net zero emission targets. The schematic diagram on the right shows enhanced shale gas recovery from supercritical CO2 fracking. On the downside, the cost of capturing and pressurizing and transporting CO2 is higher than the simple use of water. And as CO2 is a greenhouse gas, robust accounting of CO2 emissions and storage cost much more than we might expect. In addition, pressure safety at the site must be strict. Similar to supercritical CO2, it is possible to use foam as fracking fluid in hydraulic fracturing. Foams are made by mixing a gas phase such as nitrogen and carbon dioxide which is an internal phase, with a liquid phase such as water or supercritical CO2, which is the external phase. Then a suitable forming surfactant such as iodine or hydrogen peroxide is used to maintain the stability of the foam produced. The image, the slide, shows how propellant settle in fracturing fluids. And this issue is overcome by using high viscosity fluids like foam, which have higher propellant carrying capacity. Further, foam-based fracturing consumes less water, sometimes up to 90% reduction, and chemicals due to the higher foam quality, which reduces wastewater generation. Thus, more efficient and easier fluid flow back and reduced environmental damage can be achieved. However, lack of knowledge and high capital costs associated with the facilities required, including equipment and space, limit the use of foam-based rock preconditioning. Now we come to a somewhat less known preconditioning technique, electrical disintegration or plasma channel drilling. This is highly efficient rock breaking drilling technology used in the industry, and in this method, mineral liberation is caused by sending high voltage electrical pulses into the rock formations. This method can achieve high rock breaking efficiency, good borehole quality, and low drilling cost in deep wells. However, when using this method in underground mining, there are issues with the controlling generated current flow in the presence of groundwater. The large current used will most likely make the near vicinity of the mine area inhospitable. In addition, excessive heat generation might require additional ventilation, and this is costly. Let us move on to the next preconditioning technique, microwave-induced fracturing. In microwave-induced fracturing, minerals are selectively heated, which causes a thermal mismatch between different mineral grains. Therefore, thermal stresses are induced in the rock mass, and when these stresses exceed the rock strength, the rock mass is fractured or weakened. This method helps to reduce high concentration of stressors in underground mining, which minimize the risk of geological disasters. Advantages of this method include selective heating, instantaneous control, and energy savings compared with methods such as water jetting, plasma and electron beams, and laser drilling technologies. However, this method can only be applied effectively in the presence of water within the rock matrix. Next, we have a preconditioning technique generally used in enhanced geothermal system, which is thermal stimulation. Thermal stimulation is a vital reservoir enhancement technique to enhance near-well productivity in geothermal energy extraction. In this method, geothermal reservoirs, which sometimes has a temperatures of up to 300 degrees C, are subjected to cooling by multiple injection of cold water and allowing the rock mass to recover the lost heat. This creates thermal shock in the rock and generates thermal cracks along the mineral grain boundaries. However, water circulation has some drawbacks. Loss of water during circulation, leading to excessive water consumption and precipitation of minerals in the fractures, which ultimately reduce the overall permeability of the rock mass. These drawbacks lead to reduced production efficiency in the long run. More details can be found in the references given in the slide. Most preconditioning techniques have inherent challenges. Drilling and blasting and hydraulic fracturing are widely adapted in the mining industry for rock preconditioning. Explosive blasting is the most destructive method used for preconditioning, and it can generate an extensive amount of noise, heat, vibration, dust, even fly rocks at shallow depths. Pressurized fluids used to generate fractures in hydraulic fracturing can cause cross-contamination of groundwater aquifers as a result of uncontrolled fracture propagation. Further, there is a possibility of induced seismicity due to hydraulic fracking. At present, most rock preconditioning techniques have a negative public image due to the adverse environmental conditions associated with them. And therefore, hydrofracking has been banned or in moratorium in many places around the world. Other fragmentation techniques such as plasma channel drilling, microwave-induced fracking, and thermal stimulation can be challenging due to the complexity of the equipment required for fracking. Moving on to the next slide. Mineral extraction from conventional mining techniques has become more complicated in recent decades due to the decline of ore grades, difficult mineralization, and escalating demand for minerals due to the growth of the global population. Currently, energy-intensive mining operations and progressively increasing mining depths result in higher energy consumption in conventional mining techniques and adverse environmental impacts such as surface disturbance, tailing ponds, waste rock generation leading to increasing environmental and carbon footprints. For example, the current global copper usage is approximately 28 million tons per annum. This means it also produces 2,800 million tons of waste rock dust. Is it sustainable? Furthermore, with the transition to the electrification of vehicles, demand for copper will continue to rise during the next few decades. On the other hand, the grade of copper metal ore is drastically decreasing, and the current ore grade is less than 1%. With conventional mining, this will result in excessive waste rock generation, which will be dumped in even larger tailing ponds. This brings us to the environmental impacts caused by conventional mining operations. In recent history, we have seen several tailing dam failures due to the massive amount of waste rock generated in mining. The collapse of the Burumandino iron ore mines tailing dams in Brazil and that of the tailing dam of the Mount Poly copper and gold mine in British Columbia are two examples of catastrophic tailing dam failures. The far right image shows the destruction caused by a mine blast, which destroyed a 46,000 years old cultural site in Australia. The pie chart shows CO2 equivalent greenhouse gas emissions by different industry sectors in Australia from 2017 to 2018. As you can see, mining contributes to over 25% of the greenhouse gas emissions in Australia. The mining industry generates between 2 to 5 gigatons of CO2 equivalent greenhouse gas emissions annually, and most emissions are released due to the underground operations. In addition, mining causes several water pollution issues such as acid mine drainage, metal contaminations, and increased sediment levels in the streams. These lead to the contamination of drinking water, disrupted growth and reproduction of aquatic plants and animals, and the corroding effects of acid on infrastructures such as bridges. Causes of water pollution due to mining are active or abundant surface and underground mines, processing plants, wastewater disposal areas, and tailing ponds. Further, the impact of mining on biodiversity is significant. Mining activities cause physical disturbance to the landscape, contributing to the decline of wildlife and plant species in the area. In addition, chemical emissions such as mercury and cyanide used to extract gold and acids released from oxidized minerals when exposed to the air have negative impacts on biodiversity. On a global scale, carbon emissions due to mining and mineral processing activities negatively affect biodiversity due to the climate change. With the unavoidable drawbacks of conventional mining methods and declining ore grades, the mining industry will be forced to concentrate on alternative mining technologies. In situ leaching, or ISL, is one such alternative mining method. It is a non-invasive mining method which was initially used for uranium mining by the former USSR and the United States. In ISL, lixiviant is circulated through a permeable ore deposit to dissolve target minerals. Then mineral-rich lixiviant, also known as pregnant leach solution, is pumped to the surface to extract the minerals. Since this method does not require physical excavation of the ore body, ISL eliminates the energy-intensive operations of conventional mining and reduces surface disturbance. It also completely eliminates the generation of waste rock and therefore the need for tailing dams. The absence of other energy-intensive operations such as hauling, crushing and grinding compared to conventional mining also leads to a significantly lower carbon footprint for ISL. However, the use of ISL is limited to permeable host rock formations. Therefore, for industry-wide adaptation of ISL, it is essential to produce permeable ore deposit using different rock preconditioning techniques. We have already discussed possible preconditioning methods and their advantages in details in the earlier slides. Given the existing shortcomings of rock preconditioning techniques, the use of these technologies in conjunction with ISL could potentially amplify the adverse environmental effects, simply because ISL involves the injection of a highly reactive lixiviants into an ore body. This raises the question, is there a more effective technique for rock preconditioning which allows the initiation of fractures in a host rock in a more controlled manner? The answer is yes. And I will now present a novel preconditioning technique which we are developing at the 3G Deep at Monash University. As can be seen in this slide, we propose a method of injecting a non-explosive demolition agent through pre-drilled boreholes into target ore body to initiate a fracture network. The connected fracture network could potentially improve the permeability of the ore deposit and thereby increasing ISL mining efficiency. The fractures in the ore body are initiated using an in-house developed non-explosive demolition agent which we call as SREMA, Slow Releasing Energy Material Agent. SREMA is a modified version of soundless cracking demolition agent SCDA, which is a calcium oxide based expansive cement which expands volumetrically when mixed with water due to the formation of calcium hydroxide. SREMA can be used as a supplement to conventional rock preconditioning techniques to initiate controlled fracture propagation in a rock mass. When injected into injection wells drilled in a rock under confined conditions, SREMA hydration generates expansive pressure due to volumetric expansion, which fractures the surrounding rock mass. The Key ingredients of SREMA are CDA, a soundless cracking demolition agent, a viscosity enhancing admixture, a superplasticizer, and water. I will discuss these ingredients in detail in the following slides. As explained before, SCDA is the key ingredient in SREMA, and it is also known as soundless cracking agent, expansive demolition agent, expansive concrete, and non-explosive demolition agent. SCDAs are utilized for concrete demolition and rock fragmentations in densely populated areas where explosive blasting is hazardous. SCDA is a grayish, powdery, and non-explosive compound consist of cementitious and expansive components. This image illustrates the application of SCDA. SREMA is known for releasing energy slowly during the fracturing process, thereby maintaining a controlled fracture propagation compared to methods such as hydraulic fracturing. A hydraulic fracture initiates when the stress intensity factor at the crack tip exceeds the fracture toughness of the surrounding rock. Therefore, once a fracture initiates, the fluid pressure at the crack tip continues to propagate the fracture, making it very difficult to control hydraulic fractures. This also causes hydraulic fracturing to produce a single fracture plane depending on the initial stress conditions. Compared to hydraulic fracturing, SREMA charging produces multiple radial fractures surrounding the injection well. SREMA predominantly causes tensile failure due to the hoop stress developed around the injection wells. The expansive pressure generated by SREMA in a borehole develops compressive stresses in the radial direction and tensile stresses in tangential to the borehole. When the tensile hoop stress exceeds the tensile strength of the rock, a fracture is created. The expansive pressure generated by SREMA is the result of the confinement given by the surrounding rocks. Initiation of a fracture indicates the release of confinement of the rock, and a corresponding drop in expansive pressure can be observed. This figure explains the stable crack growth behavior in which T0 and P0 corresponds to the initial crack caused by SREMA. Expansive pressure drops occurs during crack propagations. The fracture is propagated only when the tensile stress applied is increased by SREMA expansion. The XRD analysis reveals that the SCDA is mainly composed of lime, halite, in addition, tricalcium aluminate, gypsum, preclose, and brown millerite. Mineral phases are present in minor percentages. When SCDA is hydrated, several hydration reactions take place. The volumetric expansion of SCDA is mainly due to the exothermic reactions of the hydration of calcium oxide, which produces portlandite. Another dominant reaction takes place when halite hydrates and forms halite hydrate. In addition to the hydration of calcium oxide, a further volumetric expansion can occur in SCDA by the formation of ettringite and magnesium hydroxide crystals, which exist in minor proportions. In addition, brown millerite and anhydrate hydration also take place. This SCM figure shows the formation of portlandite, halite, and ettringite in hydrated SCDA. The expansive pressure built up in SCDA can be experimentally measured by applying the concept of elasticity based on the principle of thick wall cylinders. A commonly used method called the outer pipe method can be used. In this method, a steel cylinder is filled with SCDA and strain gauges are placed on the outer wall of the cylinder in orthogonal directions to measure the circumferential strain and axial strain. The equation shown in this slide is used to calculate the pressure generated in boreholes filled with SCDA. This graph shows the development of expansive pressure during SCDA hydration, and the expansive pressure increases with hydration time. The variation in the rate of expansive pressure generation with varying water contents can also be observed. In addition, the initial time of the hydration process will change with amount of water added to the SCDA. Commercially made SCDAs are available in several brands like Expando, Dexpan, Brista, and Betonomite. Currently, SCDAs are used for rock breaking in several applications such as open pit mines, underground infrastructure construction, and rock slope engineering. Further, SCDAs are used in concrete demolition works. However, commercial SCDAs are hygroscopic and their usage is limited to fracturing dry rock. When SCDA reacts with a saturated rock mass, the cement loses its cohesion and washes out in the water. In addition, underground application requires the injection of SCDA into great depths. The injection process requires control over the setting time of SCDA. Therefore, we modified SCDA by incorporating different admixtures to enhance washout resistance and fluidity to make it compatible with rock fracturing under submerged conditions. The modified compound is a USA patent rock fracturing agent, which has excellent washout resistance and fluidity compared with commercially available products, which make it ideal for rock fracturing applications in underground saturated environments. In the next slide, I will discuss the modifications we have made so far. We initially obtained a patent for the modification of SCDA for enhanced washout resistance, workability, and set-off time by incorporating SCDA with Whalen gum, sodium naphthalene formaldehyde superplasticizer, and calcium chloride accelerator, and our product, as we discussed earlier, is known as SREMA. Since then, we have further improved the compound by adding deuterium gum and polycarboxylate superplasticizer. The modified SREMA has higher fluidity and improved washout resistance by combining deuterium gum and polycarboxylate superplasticizer with SCDA compared with Whalen gum and sodium naphthalene formaldehyde sulfonic acid. Now, I will move on to discuss the key benefits of SREMA. First, SREMA can be utilized in underground rock fracturing applications below the water table due to its enhanced anti-washout properties. Further, the novel SREMA has the potential to penetrate fractures at micro to millimeter scales in the rock mass due to its enhanced rheological properties. The slow energy release rate, washout resistance, and enhanced fluidity of SREMA make it ideal for rock preconditioning applications in sensitive environments. Now, let us turn to the volume expansion mechanism of SREMA. Ishalom and Bentour in expanding spheres model can be used to demonstrate the expansion of SREMA due to the formation of portlandite, which is based on crystal growth theory, and it represents the different stages of hydration of SREMA. First, the distribution of calcium oxide particles with water takes place instantly after mixing. Next, a layer of calcium hydroxide forms around the calcium oxide particles. Due to the growth of calcium hydroxide particles, the first contact between the particles occurs at what is known as the critical degree of hydration. In an unstrained environment, this initiates the volumetric expansion of cement system. Under restrained conditions, when injected into a borehole, the volumetric expansion of the particles creates an outward expansive pressure, which ultimately fractures the surrounding rock. Of the various theories reported in the literature, crystal growth theory and swelling theory can be used to describe the volume expansion mechanism of SREMA due to trindrite formation. These two theories were initially used to describe the sulfate-related expansion of sulfur-aluminate expansive cement, which is attributed to the formation of ettringite. The crystal growth theory suggests that the ettringite crystals, which form on the surface of the expansive particles or in the solution, are countable for the expansion. The mode of formation of ettringite is a topochemical reaction, as shown in figure. Here, the reaction happens on the surface of the solid without the dissolution of constituents in the solution. Expansion occurs when the thickness of the layer of expansive particles exceeds the solution thickness at a critical degree of hydration. This results in the development of contact pressure and the separation of particles. Swelling theory suggests that the water absorption characteristic of ettringite causes expansion. In this case, the reaction takes place through a solution mechanism in which the reactants dissolve and produce ions in the solution. Then the ions are combined and the resultant product precipitates from the solution, which is presented in figure B. According to this theory, an ettringite particle has a net negative charge, and the size of colloid means it can absorb water molecules to the large specific surface area. Hence, swelling pressures are developed, resulting in interparticle double layer type repulsion, causing the expansion of cement. Moving on to the next topic, I would like to discuss the factors which influence the performance of SREMA. The first factor is the water content of SREMA. This graph shows the variation of expansive pressure of a CDA with moisture content and ambient temperature. The water content is inversely proportional to the expansive pressure generated in a CDA and the critical degree of hydration. Increasing the water content increases the time taken to reach the critical degree of hydration in cement system. The manufacturer recommended water content of 30% for a CDA is a compromise between the fluidity of the compound and its peak expansive pressure generation potential. The most of water content of the compound is utilized to improve the fluidity of the system, and the amount of water required for the chemical reaction is much less. With water contents lower than 30%, SREMA can potentially produce high expansive pressure. However, this is at the expense of fluidity. The temperature is another influencing factor. It is directly proportional to the expansive pressure generated in a CDA. Temperature peaks are observed in a CDA 4 to 5 hours after mixing with water, and steep pressure spikes are generated simultaneously. The main reactive equation of a CDA systems, which is the calcium oxide reaction, is isothermic, meaning it generates heat during hydration. This heat generated further accelerates the rate of reaction of calcium oxide particles. At high temperatures, above 30 degrees, SREMA reacts. Heat could potentially cause the pre-water in the system to boil and cause a blowout. However, when controlled with the correct additives, increased ambient temperatures lead to accelerate expansive pressure generation as shown in the figures. The development of expansive pressure depends on the stiffness of the rock in which it is used. Recalling the volume expansion mechanisms discussed earlier, an expansive pressure is only generated if the material surrounding SREMA resists its volumetric expansion. The greater the stiffness of the surrounding material, the greater the generation of expansive pressures. Therefore, SREMA is most effective in fracturing brittle rock masses with low threshold for deformations. The figure shows how expansive pressure develops in different rock materials over a specific time period. Admixtures critically influence the performance of SREMA. The impact of a number of different admixtures on SCDA has been studied so far. Hinsey and Nelson investigated the workability of a CDA-based compound by adding a superplasticizer. According to their results, a CDA consists of 20% solid water and superplasticizer can produce higher expansive pressures with improved workability in contrast to the control when the quantity of water is lower than the recommended level of 30%. This is because a lower water content reduces the critical degree of hydration in a CDA system, allowing quicker initiation of expansive pressure generation. We also investigate the hydrophobicity and fluidity of SREMA by incorporating valent gum, a viscosity enhancing admixture, and naphthalene formaldehyde sulfonic acid as superplasticizer. To obtain the maximum performance of SREMA, 0.1% valent gum and 1% superplasticizer were added to the CDA. However, the addition of 0.1% of valent gum to the CDA significantly reduced the rate of generation of expansive pressure compared to the control one. This is because valent gum in the system binds free water molecules and hinders the hydration reaction. Further, some researchers, as given in the slides, use accelerators such as calcium chloride to accelerate the hydration reaction of CDA. The workability of SREMA is one of the most crucial characteristics of SREMA that requires improvement because the injection of SREMA a few hundred meters below the ground requires high fluidity for a sustained period of time. So in this section, I would like to discuss potential superplasticizers which can be incorporated with SREMA to further enhance workability. Different superplasticizers are shown in the slide and further details can be found in the references given in the slide. Next, I will focus on SREMA-induced fracture networks under different confinement conditions. As we discussed earlier, when the expansive pressure in the borehole exceeds the strength of the rock, a fracture is initiated from the borehole and propagates. However, under no confinement or axial stress conditions, fractures around boreholes propagate in four directions. This distinct fracture pattern in SREMA charge fracturing surrounding borehole has been observed in several experiments. After the first fracture initiates, the absence of confining pressure, the fracture opens up and a second fracture initiates in the opposite direction to the borehole. As the volumetric expanse further builds up within the borehole, two wind cracks are formed in a plane orthogonal to the first fracture plane. Parallel to fracturing experiments under unconfined conditions, we also carried out some numerical simulations. Numerical simulation conducted for specimens under different confining pressures using the discrete element method show the influence of confining pressure on a fracture propagation. However, under confinement stresses, a different fracturing mechanism of SREMA can be observed. The lateral restraint inhibits crack opening and translates to additional radial fractures generated around the borehole. However, the expansive pressure required to fracture the rock increases drastically with increasing confining pressure according to simulation findings. When the confining pressure increases, the failure mode of sample transits from tensile dominated failure to mixed tensile and shear failure. This is due to the confining pressure increases around the borehole. The stress states changes from pure tensile to mixed tensile and compressive stress states. I would like to point out the difference between the performance of SREMA and hydraulic fracturing under confined conditions in the near vicinity of a borehole. According to laboratory scale hydraulic fracturing and SREMA charging simulations as shown in the image, hydraulic fracturing induces a single diametrical fracture resulting in vertical splitting of the specimen, while SREMA induces multiple radial fractures initiating from the injection well. Both experiments were conducted at confining stress of 5 MPa for the comparison. In hydraulic fracturing, the generated fracture is uncontrolled and propagates continuously as long as the pressure is applied. The fracture is also sensitive to the diffusivity of the rock mass fluid, the anisotropy of the rock mass, and the directions of the principal stresses. In comparison, SREMA charging is unaffected by the diffusivity and anisotropy of the rock. In addition, the radial fractures are limited to the near vicinity of the borehole. So, fractures can be controlled by the amount of SREMA injected. Further, higher fracture density than hydraulic fracturing is achieved with SREMA charging around the borehole. Further, the impact of different injection well patterns on the fracture network generated by SREMA charge rock mass was investigated using discrete element numerical simulation. Based on the number of injection wells surrounding a central injection well, the expansive pressure development within the well and the subsequent fracture growth were investigated. The well patterns represent different repeating units for in situ leaching well field. With an increasing number of injection wells surrounding the central well, the fracture connectivity between wells was found to decrease, and consequently, a diminishing return of fracture density was observed due to large compressive stress fields being developed between wells, which limits fracture growth. Therefore, for optimum fracture connectivity and fracture density, a moderate number of injection wells, for example, 4 or 5 wells surrounding central injection well, proved to be most effective in this study. However, large variability is expected depending on the confining stresses and the well spacing. Then the fracture performance of SREMA in jointed rock mass was assessed by experimental analysis of sandstone specimens with artificially created joints followed by some numerical simulations. Further, we investigated the effect of pre-existing fracture density of rock mass on the performance of SREMA. SREMA fractures do not progress beyond a continuous fracture due to tensile hoop stresses. But for non-persistent fractures and fractures at an angle to the borehole, an extension of pre-existing fractures can be observed in the form of shearing due to the stress fields applied by SREMA. Therefore, SREMA can further propagate fractures in an already fractured rock medium, while hydraulic fracturing can lead to fluid leak off without fracturing. The fracture density of SREMA fractures increases with increasing pre-existing fracture complexity due to the increasing number of shear fractures and tensile fractures. Next, I would like to discuss the further development and industry-wide adaptation of SREMA. As we discussed earlier, SREMA is an alternative preconditioning technique for underground mineral extraction applications like in situ leaching, which requires the injection of SREMA at a greater depth in the rock mass. However, SREMA produces hydration products such as calcium hydroxide, which remains in injection well as a residual materials. These essentially work as plugs and hinder ISL application following fracturing. To overcome this problem, hydraulic acid can be injected into the injection well to digest the hydration products. Currently, research studies are being carried out in our group at Monash University. Then the remaining products and then HCl can be pumped back to the surface, enabling the injection of liquefactant into the injection wells to recover the target minerals. There's a potential for the manufacture of SREMA from waste materials from industrial applications. The primary ingredient of SREMA is calcium oxide, which can be sustainably sourced from steel furnace slag produced around the world, although further refinement may be required. Further, SREMA may be successfully adapted in other industries such as oil and gas extraction applications due to its enhanced properties of washout resistance, fluidity, and controlled fracture propagations. Finally, I would like to point out the future applications of SREMA to mineral and hydrocarbon industries. SREMA is a technology in its infancy stage which can be used to complement existing methods of rock fragmentation. There is a potential to develop a hybrid preconditioning technique with SREMA and fluid-based fracturing. Multiple fractures surrounding borehole can be first initiated with SREMA, followed by the application of fluids, which could be water or carbon dioxide, that can be used to grow the initiated fractures in multiple radial directions. However, extensive research is required for industrial application of the technology.
That's the end of the lecture, and I hope it gives some useful insight, information on various rock breaking methodologies. Thank you for listening. New research findings of slow release material agent or SREMA and other preconditioning methods can be found in our website 3gdeep.com. Please do visit if you are interested, and if you have any questions, please do contact me using the following contact details. Thank you.